Hey guys, new week, new quiz. So this week we're getting into carbonyls. Before I get started, I just do want to talk a little bit about the state of the class right now. I know there's this current sentiment that things are getting really difficult and there's a lot of material, and the thing is that's really true. To be honest, 8B is one of, I mean, if you to kind of put it in perspective, 8B is supposed to be the combination of 118B, 118C, or 128B, 128C, whatever you want to think. It's supposed to be the culmination of those two classes sort of condensed super fast into one quarter. Usually there's three classes, right? But you guys are only two. So there is a lot of material and you guys are going through it really fast. I mean, the point of this class is not really to teach you anything or actually have you learn organic chemistry. It's to kind of test your ability to problem solve and work under stressed environment, I suppose. So really don't feel bad if you're starting to feel like, oh my God, week 5, it's kind of creeping up, things are getting a little difficult. And yeah, it is going to be difficult. You guys are kind of speed running through what is usually a marathon, right? And you talk to anyone who's run a marathon, they'll tell you that's exactly what you're not supposed to do. Okay. So really what I want you guys to focus on, and what I will start to focus on too, because again, these videos, if I go through them in depth, they're going to be way too long. Got to start focusing on problem solving and looking for patterns. The best way to do well on these quizzes is to get down the major pattern, so that when you see these problems in any novel situation, right, like it shouldn't really need to be that either me or you guys or the ATC, so like it shouldn't be that someone guesses a question on the quiz, right? It should really just be you guys know the common pattern and you can apply it to any situation as long as you know the chemistry that works behind it. Okay, so I'll do my best to keep this under 2 hours. My aim today is an hour 30. So we're going to aim for that. If not, it's okay. But that's the aim for today, is an hour 30. And we're going to focus primarily on problem solving, and primarily on what are those cues, or what are those patterns that we're looking for? What are ways that we can quickly predict the product, quickly predict the answer? Okay. So with that being said, right, we're going to look at today the carbonyl family, right, the C double bond O, and its various reactions. But as always, before we even get into reactions, it's just good to understand functionality and reactivity and whatnot. Okay, so carbonyl, C double bond O, right? Beginning of the quarter, we looked at the C single bond O, so the alcohol. Actually, we can even talk about our first reaction now, right? For any of you that want to think about this for a second, you can, but there's two ways to kind of achieve this, right? You can either do chromic acid, that's aqueous, right? Or you can do the PCC version, whatever you want. Either one works. But carbonyls are oxidized forms of alcohols. And so if you can imagine, right, alcohol that has a single bond to O, you can imagine oxygen wins that tug of war on the electron, so there's some polarity in that bond. Well, now with this oxidation with two of these bonds, carbon is losing out crazy, right? So you can imagine that there's higher dipolar moment going through that carbonyl structure. Okay, so carbonyls are sort of enhanced alcohols, especially with their pi bonds. So they have sort of an enhanced reactivity. If we wanted to, actually, we can even think of the pi bond. I mean, the pi bond is kind of a weak bond. It really gets pulled on the most, right? You can imagine that the pi bond electrons are sort of polarized extremely in the sense that I can draw a polarization, or you guys might think this is a resonance form. I kind of don't really think of it as that way because resonance requires 3 p orbitals. So if there was a third one here, maybe we could talk about resonance, but there isn't. So technically this is a bond polarization, just a nitpick on my end. But you can imagine that pi bond, right, is polarized towards that oxygen, such that we have an O minus and we have a C plus. Okay. So a big part of the reactivity in carbonyls is that the pi bond can actually move, right? It clearly, those electrons want to be on oxygen. So we have a really nice O minus and this really interesting C plus. Now, way back when, maybe even in the beginning of the quarter, I might have mentioned something, or maybe even last quarter, I might have mentioned something to you guys, which was this idea that all organic reactions are some minus going towards some plus, right? So some minus attacks some plus. If I wanted to put some technical terms, right, that's a nucleophile attacking an electrophile. So some nucleophile donates electrons to an electrophile. Well, if I look at a carbonyl, right? A carbonyl has both those components. We have an electrophilic component, which is this carbon here, and we have a nucleophilic component. So you can imagine that in a carbonyl reaction, something could attack at the O minus. And as we'll see in this class, it's usually a proton. Usually what it is it's a proton that's attacking at this center. So we usually protonate on that O minus there. So to some extent, these are basic electrons, so somewhat basic. I'm saying somewhat because I don't want to give this idea that all carbonyls are basic. That's not true. We'll learn in the next unit, especially what are really the most basic carbonyls. And the two that we're going to talk about today are not really that basic. They are just, by convention, just because it's available, right? We can say that it is basic. Okay. Anyways, somewhat basic. So we can, attack with the O minus as a nucleophile. But a majority of the reactivity that we see dictated in this section, right? What are carbonyls doing the most is that they're being attacked at their electrophilic center. So anything that is nucleophilic, so you can imagine oxygens, nitrogens, as we'll see, R minuses and H minuses. These are basically the four major classes of nucleophiles. These four major lone pair donators, right? These four major nucleophiles are going to attack at this carbonyl center. And that's really what dictates most of the reactivity. Because if you think about it, I mean, again, carbonyls, really what we represent them as a C double bond O. It isn't really that we unveil either of these reactivities, the positive or the minus, until a nucleophile attacks this carbonyl center. So a lot of our carbonyl reactions are going to proceed, I mean, all of them actually are going to initially proceed as some nucleophile attacking on the carbonyl center. Okay, so if we look at this, this is a trigonal carbonyl, right? Trigonal planar carbonyl. Once attacked, it turns into a 3D tetrahedral intermediate. Okay, so this is the tetrahedral intermediate here. Okay, and so I've kind of kept these two groups here ambiguous because at the time, right now, it doesn't really matter what they are. Okay, so carbonyls can be attacked. And that is when we unveil this O minus here, right? That unit that we said can be somewhat basic. Now, as we'll see with this unit as the next unit, what happens next can be variable, right? So this first step, every single carbonyl reaction will do this, right? Nucleophile attacks at the carbonyl. But what happens next depends on the type of carbonyl that we talk about. The two carbonyls we're talking about today, their tetrahedral intermediate is usually relatively stable. So what does that mean? What does it mean to be stable in this context? Well, in this context, what it means is that the O minus doesn't want to collapse and kick off some other group, okay? Whether that be the nucleophile or it be one of the two groups here. So imagine if we had some kind of X group here that was like a leaving group, like maybe we use like a chlorine, right? We learned chlorines are the best leaving group, right? If there were like a chlorine, right, this tetrahedral intermediate will be considered unstable because the O minus would just come down and kick off that chlorine. It's the best leaving group. Sorry, it's the best leaving group we've ever seen, right? But there are some carbonyls, the two that we'll talk about today, who don't have a good leaving group. Usually it's either some like R group or a hydrogen, right? So again, worst leaving groups ever. I'll just put two R groups here. So this here is a functional group we'll talk about called the ketone. But in this case, this intermediate is stable because when the minus comes down, it doesn't really want to kick off anyone. Okay. Now, yes, sometimes it can reverse and kick off the nucleophile. That's totally possible, but that doesn't move our reaction forward. So we'll talk very briefly about ways that we can prevent this from happening, just conceptually for vocab. But generally speaking, we assume that the nucleophile isn't what's going to get kicked off. But if I look at this, whether this is R or H, neither want to get kicked off. So this tetrahedral intermediate is usually very stable. With this being the case, right, then we can go ahead and protonate on that O minus, right? Like I mentioned, that usually O minus is a nucleophile towards hydrogen, towards a proton. And what we'll get is this intermediate here, okay? This nucleophile alcohol intermediate, okay? And every single reaction we see today will have this intermediate as part of the process. Now, will it be the final intermediate and be the final product? Not always. Some reactions it will, some reactions it won't. But for every single reaction we see today for our class of carbonyls, which are going to be the ketones and the aldehydes, we will always see this intermediate being formed where the nucleophile adds on the carbonyl. Okay. So what we call this is a nucleophilic acyl addition. Okay. Now, when I talked about before, if we had a chlorine here, right? So let's say that there were a chlorine here and the minus comes down and kicks off the chlorine. That would result in the reformation of the pi bond, right? Oops, sorry, not that there. Be a nucleophile here. Right, there we go. Okay. Now that's when the nucleophile kind of replaces whatever that leaving group was. This would be a nucleophilic acyl substitution. This is the topic of quiz 5, I believe. We're on quiz 4 right now. This will be quiz 5. But it is good to still know that it exists, right? So that you have that primed knowledge when we get into it next time. Okay, so that is possible, but at the time, at this current time, we're going to just focus on the acyl additions, right? Ketones and aldehydes who's, don't have access to a leaving group. So when nucleophiles add, they stay on, nothing comes off, and that O- gets captured into the alcohol, forming this sort of alcohol nucleophile intermediate. Okay, and again, this can continue to go forward. We'll see with majority of reactions, it will continue forward. Right. But the important part is that we can get to this point here and then the reaction kind of goes on. Okay, cool. So that is, sort of again, always we want to look at a generic mechanism. This is sort of the generic mechanism we'll see for this class, at least for the first couple steps. We will have a little more. It's going to go a little more in depth with some of these, but that's OK. No need to fret on that. OK. Now, before we get into the reactions with these 4 nucleophiles to kind of understand what's going on, let's just talk really quickly about the different reactivities. Because I mentioned, we have ketones, which are, 2 carbon groups, so like 2 CH3 groups flanking a carbonyl. But we can also have aldehydes. So these are our 2 carbonyls where we don't have a leaving group, right? These are the ones that we don't have a leaving group. And so they will primarily function by addition. So we have ketones and we have aldehydes. Okay. Now, again, both of these are the same class, but they are going to be slightly different, especially when we think about reactivity, right? Which one might be the first one to react? Let's say if we had a ketone and an aldehyde on a molecule, right? Which one might be more likely to react before the other? This is actually a question that's asked all the time. In higher level organic chemistry, at the research level, at the graduate level. So if you can answer this question, you can also answer questions that your grad TAs are expected to be able to answer, okay? Which is, I think that's pretty cool. Okay, cool. So how can we determine which one is more reactive? Well, again, if the first step, the basis of the reactivity is a nucleophile attacks at this carbonyl center here because the positive, then maybe we can examine which positive is more reactive. Or another way of thinking about this is which positive is less stable. So I can draw my ketone here with its 2 alkyl chains. I have CH3, so technically this is an acetone. That's a common name if you want to know it. It doesn't matter what these are. They could have been longer, no big deal. We're just going to go with the simple example first. And this here, where we have an aldehyde, we just take that same starting point. So acetone, because ketone, it's an acid ketone. If I wanted to make the aldehyde, I make the acetaldehyde. I don't know how to say that in a different way. But anyways, we just put the acete part on the top of that. Okay, so this is acetaldehyde. Okay, so again, looking at these positives, we might want to consider which one is more reactive, which one is less stable. Okay, if I look at the ketone, right, and I imagine, this positive charge here, again, carbocations are sextets, right? They're always looking to steal electrons from any source that they can. Now, from the oxygen, they're not really going to steal very much electrons because the electrons are really happy on oxygen. So those electrons kind of, there, and it's also the same on both of them, so we wouldn't have really made a difference between them. But what might make a difference is these alkyl groups, right? Maybe we can remember a certain effect back from 8A, where if I had sp3 carbons flanking, a carbocation, those sp3 carbons really wanted to donate into that center, right? So I have 2 of these effects here. I have 1 of these effects here, right? For those of you that might not remember or do remember, this is what we call hyperconjugation or hyperconjugative effects. Okay, so we can have donating effects from sp3 carbons into carbocations. And so if the ketone has 2 of these effects,
aldehyde has only one, you could imagine the ketone has more stabilizing effects. So these are stabilizing effects. And so if the ketone has more stabilizing effects, then generally speaking, aldehydes should be slightly more reactive than ketones. Actually, not slightly. It's actually a big deal. I don't know why I said slightly. Okay. So donating effects will make carbonyls less reactive because that carbonyl cation that nucleophiles are attracted to is not going to be that strong if there's a lot of donating effects. Okay. So you can imagine usually ketones will be less reactive than an aldehyde. Okay. Especially alkyl ketones, alkyl aldehyde. So when we only have alkyl groups. Now you can imagine on the aldehyde, we still have an R group here that can donate, but there should be some aldehyde where we have two hydrogens, right? So, a perfect true aldehyde. This here is what we call a form aldehyde. Okay. So formaldehyde, which has none of these donating effects, you can imagine is going to be way, way, way more reactive. What's really interesting, actually, just a little side thing here, is that formaldehydes are so reactive that usually what you'll see is, remember, there is a positive and a negative part of every carbonyl. What will happen is that these formaldehydes will start to polymerize. So it's really hard to have free formaldehyde in solution because they're so reactive. They have absolutely no stabilizing effect. These carbonyls will just start to polymerize, and you can imagine we'll make these sort of, I forgot what you call these. I think they're called like glycol. No, not glycols. There's a name for these. I don't remember, but we can make these polymers. Or I mean, not that you want to make them, but that's what you'd have to deal with. And so usually what people will do is they'll run these on special kind of columns or special kind of materials so that it will prevent the polymerization. So you have free formaldehyde if you need to do reactions with formaldehyde. So really this reaction kind of sucks, but cool little thing to know. Right. Cool. So you can imagine formaldehyde more reactive than any alkyl aldehyde and definitely more reactive than any type of ketone. Okay. Now there's one last thing to kind of understand here, and it's again, I don't want you guys memorizing things. I want you guys understanding things, right? What we're using to explain reactivity currently is that alkyl groups like to donate. So if they're donating in, they're going to stabilize the cation, right? And so the number of these donating effects kind of determine how stable it is. And with formaldehyde, absolutely no donating effects. So what if I had a ketone that had, instead of CH3, CF3? Interesting. So I have a CF3. If I have a CF3, well, hey, those fluorines are going to be inductively pulling instead of inductively donating because fluorine is the most electronegative atom. So if I have a pulling effect on here, then hey, I'm actually going to have a pulling effect on the carbonyl as well because fluorine is going to start to pull on these pi bond electrons too, right? It really wants those electrons for itself. So instead of inductively donating, CF3 groups are going to inductively withdraw. And you can imagine this withdrawal effect, if I were to kind of highlight the cation in all these examples, right? The cation here might be very small, might be a lot, larger here, might be larger here. You can imagine here, it is the largest, absolutely the largest. Oh, you know what this looks like? This looks like that, that one thing, what is it called? From Final Fantasy. I forgot what these are called. If anyone can remember, please let me know. But that's what that reminds me of. You can imagine we have this huge dipole on this carbonyl center, despite being a ketone, right? Despite it being a ketone, it has a huge, huge, huge dipole on there, huge cation, definitely going to be the most reactive out of all of these. So don't just memorize that, oh, aldehydes are better than ketones. Understand what makes them better, right? Because then you can look for these effects and they can help you rationalize. If you have to choose between sorting who is more or less reactive, right now you know what to look for, right? Look for withdrawing effects versus donating effects, okay? Now, generally speaking, between ketones, let's say you had just alkyl ketones and you had several of them and you're trying to understand who is better and who is worse. Again, they all here have the same donating effect. So, I mean, I can quickly just mark it with lines. They all have two donating effects. So once you've kind of looked at the electronic effect, which is donating or withdrawing, at they're equal, then you look at steric effects. So who is just more bulkier? Generally speaking, the less bulkier your ketone, the better it is suited for attack, right? Imagine a nucleophile that's kind of zipping around, has a way easier time attacking this carbonyl here than it does, when it kind of runs into this guy and then, it doesn't even want to even go in there. That's like that's too many people hanging out there. So carbonyl is like this one, and you can imagine I can even make this worse, right? I could even do this. I can make it tert-butyl on both sides. This is virtually unreactive ketone. Very, very hard ketone to react. To kind of put it in perspective for you guys, I've actually worked on a ketone that kind of looks like this. This ketone is a little interesting, a little, doesn't really budge very much. It's not terrible. I won't make it seem like it's terrible, but it usually takes like an hour for reactions with this. To put it in perspective, something like an aldehyde, if you reacted with an aldehyde, probably would only take like 30 minutes, 20 minutes. That's how reactive aldehydes are. Okay, cool. So reactivity of the carbonyls that we see here. Again, if you're trying to understand what kind of question would come out of this, there's two types, right? One is that you can be asked a molecule where you have a ketone and an aldehyde, and you have to understand which one reacts first, right? Like let's say with a nucleophile, right? You can imagine aldehyde is going to react first usually. Yeah, pretty much that is always the case. So we'll see some reactions. I'll write one right now, but we'll see a reaction, something like this, where actually this is very useful in industry. We can take advantage of aldehyde reactivities. Even though there's two carbonyls, we know the aldehyde will react first. So if I want to react something with the aldehyde, I'll do that first. And then I'll work with the ketone, whatever I want to do. So we'll see in a second, how did I predict this in 2 seconds, right? Even you guys could do this. That's how simple this is. Okay, cool. The other way you can see this again is you're given a bunch of these aldehydes and ketones and you're asked to order or who is the most, who is the less, reactive. Cool. But with that being said, let's go ahead and start looking at the reactions of carbonyls. Let's go ahead and see what these guys are going to do in this class. And so again, I always do my order a bit different. You might have noticed from Dr. Levens, which is totally fine. I just take a route that I believe for myself to be logical. Everyone has a different idea. This is just mine. So I like to go through looking at the reactions. I think you guys, I don't remember how you guys do it, to be honest. I just remember you guys doing it a little different. But I always look at the most abundant nucleophile first, right? What's the first thing? If I gave you a glass of ketone, let's say I give you a glass of acetone, right? What could you put in it as the very first nucleophile? Very first nucleophile you could put in is water. Okay, so you could put in water. Oh, one other thing that I'll mention here. So generally speaking, because aldehydes are more reactive than ketones, if I describe a reaction with a ketone, it can definitely happen with an aldehyde too. So it's okay if you see me draw a bunch of ketones, or if I neglect an aldehyde in some section, nothing really changes. It just means that it's an aldehyde instead of a ketone. So I'll do this reaction here with an acetone, but we can also do this reaction with an aldehyde too. You can imagine it's just a better reaction with the aldehyde. But if it works with a ketone, it definitely works for the aldehyde. I just want to limit as much as what I draw. Okay. Actually, with that, there's one other thing we could talk about here too. So I guess we'll just mention really quickly. So there's going to be two types of nucleophiles, as we'll see. And, if we kind of like group them up together, we're going to have our oxygen nucleophiles. We're going to have our nitrogen nucleophiles versus our R minuses and our H minuses. Okay. Generally speaking, if I wanted to kind of put these two into categories, what I could put these two into categories as is these guys are sort of weaker, more stable nucleophiles. And these guys here are sort of like stronger, very, very unstable, super reactive. So what we'll see in this section is that whenever I want to react with these stronger nucleophiles, I kind of just dump them in. Like if I have a carbonyl and I have an R minus, I'll kind of just dump them in, and I won't even really worry about this, right? This will work really, really well. Maybe even a little too well. This reaction will work. And you'll notice here that I put, because I'm remembering now that someone slightly made a little tiny mistake on this, but it's okay. You might remember, or you might see these arrows here. These reactions are generally irreversible, right? Once you've added this really strong nucleophile in, it wants to stay on. It is not looking to come off at all, right? That's never a option for this nucleophile. So usually these irreversible conditions, we use single head, or we just use like one arrow. Don't have to really do much here. Just throw these two things together and just let them react. Works really, really well. A very good cue for this is that these are usually very strongly basic. Like I know that you guys have an idea of what a strong base is, but I'm talking take your strong base and make it 20 times, 30 times, 50 times stronger. This is what we're thinking about. when we think of a strong base. So in this category will be like the R minuses and the H minuses. So you'll notice that with these guys, we don't really have to do much, and just got to kind of breathe on it and it works. When it comes to oxygen and nitrogen, though, we kind of have to massage these guys a little bit. Usually what you'll see is that we'll have to add in some kind of catalyst. So for example, as we'll see with the ROHs, or actually even with water, we can even start with the water one now. What we'll usually have to do is add in like a base or an acid catalyst. And both of these kind of take slightly different routes. So if I have an acid catalyst, in acid, you should always protonate something first. We'll protonate that carbonyl that I mentioned is somewhat basic. And now this carbonyl with the positive, right, more activated, now water will go ahead and attack. Initially, we'll have this here, but something will pick up that proton in solution. And now we'll get our adduct for this reaction. So these guys are a bit more reversible. We call these reversible conditions. A lot more stable, these nucleophiles. Usually, again, you have to kind of promote them or motivate them to do a bit of reaction. These are usually, I'm going to say weakly basic here. But remember, this is in context to these very strongly basic nucleophiles down here. These guys are insanely basic. So anything in their face is weakly basic. I know you guys remember OH minus and like N minus to be pretty strong bases, but in the face of these guys, they're kind of nothing. They really aren't that. They really aren't that, crazy basic. Okay. So kind of an idea when we look at these reactions, because I realized I wasn't going to mention this. I was just going to draw them, but I don't want you guys to be confused. I want you guys to, again, understand all the chemistry. So this here would be sort of like the acidic condition, right, where we kind of protonate first, and then we add something on, and then we move on with our day. Okay. The basic condition would just look like, instead of protonating first, we have OH minus, very strong nucleophile. And then something in solution will just protonate this. So luckily for us, basic solutions are a bit faster to draw out. So cross our fingers that we get a basic solution on the exam, or sorry, on the quiz, right? Cool. Anyways, this is going to be the general pattern. Again, general mechs are good to know, good to have an idea of, right? We're going to see a lot of reversibility arrows for the O and the N's, but when it comes to the R minuses, H minuses, we won't really see much of that at all. Okay, cool. So again, let's say I gave you a cup and I filled it with acetone. What's the very first reaction you can do? You can open your faucet, or you can turn on your faucet. That's a really bad faucet. Anyways, you could turn on your faucet and you can pour in some water. That is the very first reaction you can do. So what happens when I have, add water to a carbonyl? Well, as we kind of saw a second ago, right? What'll happen is to your carbonyl, water will go ahead and add. So let's say that we're doing this reaction in acid catalyst. Again, anytime you're in acid, the first thing you should do is just protonate something. Very, very good idea. Because once you protonate, you've turned this O neutral into O positive. Super, super, super juiced up dipole right there. So if I had some dipole here, you can imagine it's incredibly more reactive here. And now water, usually a weak nucleophile, very, very motivated to go ahead and do its attack. Okay, so what we get out is this tetrahedral intermediate. Again, something in solution will pick up this proton. So that proton on the H, something will pick it up. I will do this once and then be lazy for the rest of the video. I'll let you guys know right now. Right, this is how a proton transfer would look like. But what we get out is this molecule here, which if I wanted to redraw it, could look like this. Okay. So if I look at the difference here, essentially what I've done is I've hydrated the carbonyl, or I've taken that carbonyl on that center, kind of gotten rid of it, and what I replaced with it is two alcohols. Okay, so this is a diol, and because the two alcohols are on the same carbon, we call this a geminal diol, or another term you see is hydrate, because again, you've added water, you've hydrated it. So geminal hydrate, geminal diol, same thing. Okay, I know I've mentioned this a couple times. I'll mention it again. A very nice way to remember geminal is the astrology thing where Gemini, the twins, right? These carbons have two alcohols, so the alcohols are twins of each other. It's a nice way to remember it. Okay, cool. But hey, I can add water and I can make geminal hydrates. Okay, and so we can also do this in base. It's a little bit faster because we have OH minus, so no protonation required. OH minus is a juiced up nucleophile. So either you activate your carbonyl or use an activated nucleophile, right, in these reactions. And what we get out is this here, which again, something will protonate this, usually just water in solution. And what we'll get out again is a geminal hydrate. You can also just redraw this to look like this. It doesn't matter. Do whatever you want, right? I'm just drawing them a certain way. Okay, cool. So we can hydrate our carbonyls. Now, the question is how stable is this, right? Like how, is this something that I would expect? And the reality is that general hydrates are not very reactive, are not very stable. OHs, as we'll see, and I really implore you guys, I really push you guys to remember this. OHs in this section are very, very volatile, especially if you can make them into water again. So anytime you see an OH, it is very likely the case that you can push it forward and get rid of it. Or push it backwards and get rid of it. So especially in acidic condition where you just have to protonate this, it's very much on the side of, add the water in and then you get rid of it almost immediately. So usually not very stable. These are usually unstable intermediates. But general hydrates are still very interesting and they're still very useful because they can tell you how reactive a carbonyl is, right? If this reaction functions on an equilibrium, all you really have to test if you want to know how reactive a carbonyl is just put it in some water and see how heavily the arrow is to the right, right? So let's say I have some ketone with R1 and R2, and I wanted to see how, reactive it is. All I do is put water in here and I just kind of calculate the concentration of the hydrate, right? So if I know how much of the ketone I put in and I see how much is lost or how much of the hydrate is forming, I can tell how reactive that carbonyl is, right? Because usually more reactive carbonyls are going to be the more hydrated carbonyls. They hydrate a lot easy. Formaldehyde, for example, as we mentioned, being more reactive than alkyl ketones, alkyl aldehydes, right? You can hydrate this really well. The arrow is very much to the right or towards the hydrate in this example. And you can imagine if this guy works, right, that CF3 example works as well, right? If I have a CF3 on that carbon instead, very, very hydrated, that carbonyl. Here's an interesting one, actually. There was someone in your class that was a little, I won't say upset, but they were a little bit like, oh, Jim never asked us high-level questions, but he's always asking 118 high-level questions. It's because I don't want to bother you guys. I just want you guys to get through this class. But, I'll go ahead and ask you guys a high-level question. But this here also has a very, very high hydrate concentration. And you might want to sit there and maybe think about this for a second. The answer is not very obvious initially. I'll tell you what, it's an 8A answer. The answer to this relies on 8A chemistry. But you can go ahead if you want. You can put this on the side of your paper. You can think about it. I'll answer it at the end of the video. But you'll want to use 8A chemistry for this. So you want to use some kind of, it's nothing complicated. Really, the answer is very simple. You just have to kind of think about it. I'll give you a hint. It has to do with, obviously the shape has something to do with it, right? The triangle is causing this effect to occur. But the question is how. Cool. So I can add water to these systems, can hydrate them, that can form these geminal diols. But again, usually this is not what you want. These are very, very unstable intermediates. You'll usually, if you do this reaction, you're doing it to test reactivity, not much more than that. So don't really expect yourself to be drawing geminal diols as answers. You're really just going to be looking at them as like a thought experiment, right? If water can add, then maybe I can add other things. For example, what if I just took my water and I made it organic, right? So if let's say I go to the store and I buy a very tall bottle of whatever is really good liquor now. I don't know. When I was a high schooler, it used to be Smirnoffs. That's what everyone wanted to buy was a Smirnoffs. Okay. So what if I took alcohols and I did the same reaction? Okay. So you can go ahead and we can look at this in acid and in base. But let's say that I had alcohols. Okay. So let's do the acid condition first. So again, anytime you're in acid, just protonate something, or obviously just protonate the carbonyl. Right, so we can go ahead and protonate the carbonyl, and have the alcohol go ahead and add in. So far, so good in terms of, following everything we've kind of talked about in terms of reactivity. Again, something will pick up that proton. I'm just lazy. I'm not going to draw it. But what we'll get out is this intermediate here, which is the OR and the OH. Okay, so we have this structure here, half alcohol, half ether. What we call this is a hemiacetal. So I'm going to start using this terminology. We call this a hemiacetal, which means half acetal. So you can imagine that there must be a full acetal, but we'll get to that in a second. Okay. So we can add alcohols to carbonyl centers to form these half ether compounds, half alcohol, half ether. You can do the same thing actually with base 2. So the base form would just be RO minus ROH. And what we'll get out is this will attack here. Same compound, the same hemiacetal compound. Okay, cool. Again, crossing our fingers, the base mechanisms are really fast, right? It's just 2 steps. So really, really hoping that we get that on the quiz, don't we? So it's so fast. Okay, cool. So we can add alcohols to our carbonyls and make these hemiacetal structures. So again, question becomes, how stable are these molecules? Turns out hemiacetals are just like hydrates, not very stable. Again, you're not really going to expect to see this kind of molecule as an answer. Well, maybe you might. We can talk about one example where you might. But generally speaking, these guys are usually unstable. And you can imagine why, right? What we just talked about. We talked about how if you have an alcohol, right, you can just turn that into water, or you can just kind of get rid of it. So in the case of base, right, this can just, collapse back out. You can kind of get rid of it, go backwards to the carbonyl. In the case of the acid as well, right, we can kind of, get rid of the alcohol, go back. Okay. So generally speaking, again, if you're drawing a hemiacetal on your paper that looks something like these two, maybe you don't want to do that. Maybe that's not exactly what you want to be doing there. But there is one kind of hemiacetal that is isoluble. So there is one that is isoluble. I'll go here and put your exception. And that is this type of hemiacetal here, which hopefully when I start to draw this, start to think, it's that example, right? It's that iconic thing, the tethered alcohol to my electrophile, right? So I have an alcohol tethered to my ketone. What's going on here? Well, hey, let's say that I go ahead and put in H2SO4 or H+, right? Again, I can protonate this. What's going to go ahead and attack that carbonyl? Who is tethered? That's a really good nucleophile in this instance, and will beat any nucleophile in solution. Guys, it's that intramolecularity, right? So intermolecular reactions, we're going to see these. I told you, we're going to see these all throughout the quarter. Intramolecular, move out the way. Okay. Intramolecular. Okay. So again, my counting style is the following, where the oxygen that attacks is oxygen 1, where it attacks is carbon 2, and then everything in between. So 3, 4, 5. So what we're going to get out is a structure where oxygen is going to be in it because it attacks. 1, 2, 3, 4, 5. 2 is the carbonyl that I attack, so there should be an OH here. Okay. And on 2, there's also this methyl as well. So I'll go ahead and add that in. Okay, so I'll get that methyl in there. Okay, but here is a cyclic hemiacetal. Okay, and cyclic hemiacetals are very, very stable. Very, 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 very stable. Okay, mainly because of the fact that they're a cycle, right? You can think about entropy stuff for that if you want to. If you on the exam you draw a cyclic hemiacetal, you are on the right track. That is very likely what you were supposed to do. If you see an alcohol and you see a carbonyl and just acid, right? All tethered together. Cyclic hemiacetal is very, very good. The only way this really changes is if I make it 6-membered, right? So I just make it 1 carbon longer. So now again, I'll do the numbering. 2, 3, 4, 5, 6, and maybe actually now I'll do an aldehyde. Do an aldehyde here, and what I'll get out is a 6-membered ring. This is 1, 2, 3, 4, 5, and 6. Where again, 2 is going to have the carbonyl on it, or at least the OH that originates from the carbonyl, and there'll be an H here, right, for that H, but we don't have to draw it in if we don't want to. I'll draw it in though, so you can kind of trace it if you'd like. Okay, very, very stable, these cyclic hemiacetals. In fact, there's a cyclic hemiacetal we consume every single day. It is also probably one of the leading causes for what's something you guys all like. I imagine you guys probably all like boba or something like that, right? You can imagine this is the leading cause of boba addiction, right? Those tapioca pearls, right, in those drinks, right? Oh, this kind of looks like a pepperoni pizza, like as a pepperoni boba, right? Right. These balls here are made up of a hemiacetal that everyone loves and consumes every single day. That hemiacetal is glucose. So glucose, when I draw it, is going to look a little scary, which is okay. But hey, sneak peek to that final week of material you're going to learn, right? Why is it that we learn about sugars in this class? It's because if I look at all these carbons, there is a carbon here that is hemiacetal in nature, right? It is half alcohol, half ether. So this is the ether part, this is the alcohol part. Okay, so glucose, or in this case, this is alpha D glucose, or not alpha, sorry, that is beta. That is beta D glucose. Okay. Very, very famous hemiacetal. All of you should know it, should be able to recognize it. And again, it's what I looked for in here was that carbon that's half ether, half alcohol, right? That's what gave away that it's a hemiacetal. So that being said, then let's just go back here for a second and just talk about the kind of pattern that we're kind of seeing here again, right? So we saw this with the hydrate, but essentially we're replacing the carbonyl with an OR and an OH. So if you feel like you have to draw a hemiacetal as your answer for whatever reason, right? You're essentially replacing that carbonyl, erasing it, and putting an OH and an OR in its place. Okay, kind of saw that with the hydrate. Sorry, with the hydrate too. So when you see an oxygen nucleophile, this is a very good pattern to recognize. That whatever ketone I get, no matter how scary it is, very possible that all I'm really doing is replacing the alcohol with 2 bonds to oxygen, right? Now, if I'm convinced that it's a hemiacetal, I can put an OH and an OR, although I'm not really convinced right now because I mentioned that typically these are usually very unstable unless there is some cyclic action going on, right? But that's not usually the case, right? So if instead of that, right, we had maybe, something like this. Yeah, very likely, right? I mean, this is a crazy example, but still 1, 2, 3, 4, 5, 6, 7. Oh, too many carbons. Second attack there, 1, 2, 3, 4, 5, 6, right? That'll work. But there's an oxygen here, there's an OH here. Okay, cool. So again, a pattern to kind of take out there is if we see an oxygen nucleophile being used, I think I want to replace it with 2 O's, that carbonyl. Okay. So again, these are unstable. So what can I do with them, right? Will they collapse back into the carbonyl, or will they, continue forward? If I kind of get rid of the exception of the cyclic one. Well, it turns out if I have an excess of alcohol, so I have a lot of alcohol in the system, so not just one equivalent, I have a lot of these. In acid, what will happen is the alcohol will get protonated. So I mentioned anytime you have an OH, you have extra reactivity. And so extra reactivity here is that we can make water. And if you guys remember, anytime you make water in this class, you want to get rid of it. So we can go ahead and lose that water molecule. And what we get out is going to be this cation here. Okay. Now, you can imagine this lone pair next to this cation is going to help stabilize it. But what I get is this here, which I'm drawing out a particular way, because my next question to you guys is this structure down here where I have sort of looks like a C double bonded to O. Let me just write it the other way around. Right, so I'll write it this way. I have a C double bonded to O, but I have an R group on that O. I think this looks like something. I think that looks very much like something else that I just saw earlier in this mechanism. I think that this is similar to that activated carbonyl in the beginning. So that point where I said, hey, let me protonate the carbonyl, right? So it makes it more reactive towards an oxygen nucleophile. Well, hey, look at that. I have something similar. I have a carbonyl. It's just like it just looks like it's protonated by an R group. So it's not, it's not activated by H, it's activated by R. And if I just saw what the reactivity was when we have a similar structure, so when I have that O plus, what happens, right? And O nucleophile attacks, then I shouldn't be confused that the next step is going to be exactly the same. ROH is going to go ahead and attack once again. Okay, so look at that. We're using reactivity of the system that we've already seen to explain further steps. So if you know the first half of the reaction, you know the second half. You get it for free. And what I get out is this molecule here, which again, upon proton transfer, will give me this here. Which, if one ether was a hemiacetal, then two ethers are going to be what we call an acetal. Okay? And that's what happens when we add excess alcohol to a carbonyl in the presence of acid. We form these acetal molecules. Okay, so we can also redraw it this way as well. Okay, so either way will work. It doesn't matter. I just drew it this way because it just happened to be that way. But again, what we're essentially doing is we're taking that carbonyl, whatever that alcohol is, I'm replacing it with two of these OR groups. Okay, so I'm kind of erasing the carbonyl. I'm saying, hey, that carbon right there that had the carbonyl, let's put two ORs there, right? I'm over alcoholating, I guess, another way to think about it. I'm over alcoholating that carbonyl compound, or that carbonyl center. And again, the driving force of this reaction was the formation of this water molecule. So having that proton was very crucial in making the acetal. So when I look at the base type of this reaction. So I look at the base catalysis. Is there any proton for this OH to grab in a base solution? I don't think so. I don't think bases have protons in them, right? That's the whole point, is that there is not a very high proton concentration in base. So when it comes to carbonyls in base, actually, we are going to stop at the hemiacetal. We cannot make acetals in base. They are only allowed in acid. Okay. So bases will stop at the hemiacetal, whereas acids will continue forward towards the acetal. Again, the reason being this step here, this is the crucial step. This here is the crucial step in determining that, this protonation here. A very easy way to remember this is acid and acetal both start with the same letter. So anytime you see acid and you see alcohol, which also starts with the same letter, right? Alcohol and acid equals acetal. These two together will give you an acetal. Okay, so look at that, AAA. Right, not only do they give really good car insurance, I think, I don't know, the same things. They also give a very good mnemonic to remember when you should form an acetal. Acid plus alcohol gives me an acetal. Okay, acid and base gives me a hemiacetal. There's no mnemonic there, right? But that's just to remember. Okay, cool. So this is the mechanism for alcohol additions into base. Sorry, into carbonyls. And again, let's just look at how we can just kind of quickly solve some of these, right? Like if I have like this here, and I have, let's say, an ethanol in H2SO4, right? How can I quickly solve this in 2 seconds, right? How can I solve the answer for this? Well, hey, it says acid and it's alcohol, so I know it's an acetal. So all I've got to do is kind of draw the same carbonyl, get rid of the carbonyl, and then just add two of these alcohols, right? That's exactly what's going on there. So just like that, I could have a ketone that looks like this. I could add, let's say, isopropanol, H2SO4. Again, I'll go ahead and draw this here, but we're going to get rid of the carbonyl and then two of those alcohols just right there. Super simple. Look, it's not even taking us a second to do these, right? We're being limited in how quickly we write these, but in our brain, we already have the answer. That's what we're striving for. The brain has the answer, is just limit. We're just limited in how fast we can answer these. Okay. Now, again, we can have these intermolecular types. Just keep in mind, right? One equivalent of the alcohol right? So don't do this, right? You might see this and you might think, oh, okay, get rid of the carbonyl and put 2 of these here, right? This is the trick. Don't fall for this. This is not the answer. Remember, hemiacetals that are cyclic are very, very stable. So they want to form first. So if anything, we're first going to get cyclization 1, 2, 3, 4, 5. Just like that. And then because there is still alcohol in here, we can replace the OH with that OR group. So this is a very fancy example, maybe one that you might want to write down on your note card, because it's a very good tricky one, right? Where you have a acetal formation with 2 alcohols, maybe they're not the same. Usually they're the same, right? You don't really mix and match with these. You wouldn't want to do that. But in this case, you can go ahead and do that. That's totally fine. Okay. Now, there's one last alcohol that I think is worth looking at before we move on to the amines. Okay. And I'll also kind of do a double whammy here, where I'll put a ketone and an aldehyde. The other one is the one that everyone's been having a hard time with the homework on, because we've been losing a carbon, we've been adding a carbon, we've been not sure how to make the dotted lines go. This mechanism question, I've seen it so much, you guys are gonna remember that the rest of your life. But we can also have alcohols that are tethered to each other. So not only can I have an alcohol tethered to the carbonyl, but I can have a diol that's tethered to itself, right? So this diol here. So how is this going to work? Well, you can imagine that, again, first off, between these two, who reacts first is going to be the aldehyde. So this is going to go on the aldehyde. You can imagine that initially we'll make a hemiacetal where we have an OH and then we have the OR group, right? So we have that. Okay, so that's the hemiacetal, right? Is adding that. Now, again, don't make the mistake of going ahead and adding, 2 of these like this and saying, oh, this is the answer. Remember, why would I need to add 2 of these if I already have 2 alcohols on one of these? Okay, what we're going to do here is this alcohol here is just going to be the other oxygen that goes ahead and attacks, right? So when this becomes that, remember that carbonyl-like intermediate that is activated, this alcohol is just going to go ahead and facilitate attack. And we're going to get this here. Okay. So we can go ahead and form cyclic acetals that are cyclic by the diol and not necessarily by the whole molecule. Okay, so this is also a very good one to know. There's a 5-membered version where there are 2 carbons here. The 6-membered version is that there's 3 carbons in between. Sorry. So 1, 2, 3, 4, 5. That means that we're going to have, oops, did it again. We're going to have something like that, right? If it's 1, 2, 3, 4, that means we're going to have a 5-membered ring. Okay, cool. So again, if I have alcohols adding to my carbonyl, in acid, they will go towards the acetal. So carbonyl, H plus ROH. This is going to go towards my alcohol. Okay. Sorry, my acetal. If I have them in base, you can make some argument, I suppose, that this will go towards the hemiacetal. But I'm hoping that she doesn't ask this one at all, because usually you will do a different type of reaction with this. Because again, hemiacetals, unless they're cyclic, are not very isoluble. They're really in an equilibrium, and unless the carbonyl is really reactive, like the 2 that we talked about on that one page, this is not really a good answer. Really, we'll see a different case, a different use for this kind of base right at the end, or maybe in a different video. I think I might split it up into 2. But there's a different case for OR minus. Like we have a different reason to use it. So I don't really expect you guys to make acyclic hemiacetals. I don't think you guys should ever make a acyclic hemiacetal. Now, that's not to say that this couldn't work. This could have been like OH minus, and that would have been fine. So I could have also have done down here like an OH minus condition. That would have been fine, okay? Because it's cyclic. Cyclic is okay, but acyclic hemiacetal, not very likely the case. So if you find yourself drawing something like this, maybe erase it. Maybe don't go with that. But if you see yourself drawing an acetal in acid, very good job. If you see yourself drawing a cyclic hemiacetal, very good job. Okay. Now, one last thing, just so we're on the same page here, right? Oxygen is in the same column as sulfur. So whatever oxygen can do, sulfur can also do. So if I were to, for example, replace these oxygens here with a sulfur, guess what? This also just turns into sulfurs, or these are just sulfurs. It's the exact same reactivity. So because they're in the same column, we expect them to do the same type of additions. Okay, so oxygen, sulfur, kind of the same in that respect. Okay, cool. A little bit of an advanced one, but it doesn't hurt to mention it, right? Cool. All right, so that is the oxygen nucleophiles. And we're going to call it on that there. Okay, cool. So next then we can look at amines. And amines are a bit interesting. Okay, we'll probably spend a little bit of time on these just because there's quite a bit to talk about. So just a little bit of a reminder, there's a couple different types of amines. There are ammonias, which are NH3. There are primary amines, which are NH2s. Secondary amines, which are NHs, and then tertiary amines. Now, you guys might have learned in Helix's class or whatever class you took that you should kind of count how many R groups are on the nitrogen to figure out which one is better, or sorry, which one is primary, secondary, tertiary. In my opinion, it's easier to just recognize the H's, to recognize NH2 as primary, NH is secondary, and N is tertiary, and then NH3 is ammonia. That is just my way of doing it because, in my opinion, it's just easier to see NH2 because it's written out than it is to just count the number of alkyl groups. Just to me, it just works. It works better for me that way. Okay. So these are our amines, and again, ammonia. This is primary, secondary, and tertiary. And really, our reactivity can be kind of split up into two parts here. Really, kind of three, but two. But you can imagine that these guys are going to react a little more similar, or similar to each other. This guy has its own type of reaction, and then we'll actually see that this guy never reacts at all. Okay, so let's go ahead and look at this reaction. Again, I'm going to go ahead and use a ketone here, but it doesn't matter, right? The ketone doesn't matter at all because if I show you on a ketone, it means it works on an aldehyde too. Okay, so let's go ahead and look at the reaction with ammonia. What's going to go on here? So again, usually you need to motivate these nucleophiles a little bit to get them to react. In the case of ammonia or amines, we're only going to see acid catalysis. So thank God we're only going to see acid. Okay. I mean, technically we also only see acid here too, because again, the base reaction has a different use case. Same thing here. If I use base here, we'd see a different use case that we don't want. So only really going to concern ourselves with the acid mechanism here. Okay. Now, I know that you guys probably learned that you go ahead and protonate the carbonyl first, but I'm a very big stickler on learning things correctly. And if I think about O versus N, and I think about my basicity trend from 8A, N is more basic than O. So actually, the first step should be that the nitrogen is what gets protonated. Okay, so nitrogen gets protonated first. And you might be thinking, well, that doesn't help us, right? If anything, that kind of ruins the reaction, doesn't it? Because we want to protonate the carbonyl. And that is true. But the point is that immediately you get a nitrogen protonation, and slowly the carbonyl and the protein swap. So the carbonyl will just take a proton from the nitrogen. And as it takes the proton from the nitrogen, it also frees up that lone pair on the nitrogen as well. So as you activate the carbonyl, the nitrogen also becomes activated, and then it gets back a lone pair, which the nitrogen graciously donates right back into the carbonyl. Okay, so the carbonyl got a full return in investment there, right? It gave up an electron lone pair to give to ammonia, right, for that proton, and then ammonia said, "Hey, you know what? I'm actually your undercover boss. You didn't have to do that, so I'm going to go ahead and give you back your electrons." And what we get out is this here. So again, initially we'll have a protonation here, but something in solution will pick up that proton. And what we get out is this here. So again, we have a hemi structure. In this case, what we call this is a hemiaminal. Okay, so you might be thinking, oh, so the whole thing is called an aminal when we do this reaction. Not actually. It's kind of funny. It's not actually going to do that. But this is a hemiaminal. And again, usually these are very unstable. Usually very, very unstable. You don't really ever see hemiaminals stabilized. There are some cases where they are, usually not very often. But again, if I have an excess of this kind of structure, of this kind of ammonia, you can imagine that we can keep going here. especially since we have an acid and we have an alcohol, right? What did we just talk about, right? Acids and alcohols, we can get a loss of water. So I just realized I kind of put two steps together in there. It's okay. There should be a protonation step and then the loss, so don't forget about that. I've already gotten an A in my class, so, or sorry, never mind. I haven't even taken this class yet, so I can do whatever I want to do. So anyways, yeah. So remember, there's two steps here. Protonation first. I guess you can put it on the same one, whatever. But yeah, make sure this is like two different steps, the taking and the giving. Cool. But again, we can lose water and nitrogen can go ahead and donate in. So what we get out is this here. Okay. So we get out this structure here. Okay. Now, last time when we had a structure similar to this, right, where we had sort of a, again, I know I've been drawing kind of upside down, but I'll draw it right side up. But last time we had something like this, we said, hey, so when I had oxygen sort of positively charged with that R group, we said, hey, another alcohol can go ahead and act as a nucleophile on this system and add in again. Because alcohol is really the only function alcohol has in that solution is acting as a nucleophile. So alcohols are kind of limited. They can only act as a nucleophile. So that's why we always saw attack on that carbonyl center there. Amines, though, are a little different because amines, not only can they act as nucleophiles, so you could totally make the argument that this could happen here, but amines are also pretty good bases. So not only could you have an attack on the carbonyl center, but you could possibly also have an attack on that hydrogen as well. Question is, what are amines better at doing? So maybe some of you know this answer, maybe some of you don't. But I did mention something earlier, right? There's a reason why I did that first step at the beginning. It was to prime your brain, right? I've taken psychology classes. I primed your brain to an action so that it doesn't seem as foreign. What was the first thing the ammonia did before it even set on attack? It took the proton, because amines are good bases. So look at that. Amines are good bases. So when I ask this question of is arrow A versus arrow B better for the next step, which one is it going to be, right? What does my priming tell you? Hopefully my priming tells you that it is in fact that B is the better arrow where we get rid of the proton on the nitrogen. And in doing so, what we form is the imine structure. So this is known as an imine. So it's kind of funny, right? This is called a hemiaminal. I guess the reason why it's not called an aminal is because an aminal would give you the, this would be an aminal here, right? But we don't even form that. What we form is the imine. So we form an imine structure here. Okay. So this is the ammonia imine, which if you kind of look at it, if I kind of compare it to the carbonyl, all I really did was I erased O, I put an N and an H. So any reaction you do with ammonia, you're just replacing O with an NH. Super simple, right? So in this reaction, I went from NH3 to NH, so I lost 2 hydrogens. So you can kind of see why I drew the parallel between ammonia and primary amines, right? Because both of these, right, if all you're going to do to make an imine is lose 2 hydrogens, both of these have 2 hydrogens. So you can imagine, so if it's for NH3, we go from NH3 to NH, then RNH2 is going to go from RNH2 to RNH, okay? Or if I were to kind of describe it on the carbonyl here, to go from this to the primary amine adduct, all I'm doing is putting R and then N and then whatever the R group is on that nitrogen. Okay, so primary means super, super, super easy to predict. You are essentially, so let's say I have this guy here, and I have ethylamine in acid. All I'm doing is I'm taking my carbonyl structure, erasing oxygen, and putting N and then whatever R group is on it. Okay. Now, if I were you guys, I wouldn't really worry about where I put the R group there. Technically, there are 2 isomers here. In a higher advanced class, you would need to know which one is more stable, which one is more likely, right? Especially in acid, which is what we call an equilibrating solution, equilibrating thermodynamic condition. One of these is better, but who cares in this class, right? We just want to predict the correct answer. Either one of these will probably be accepted. If you want to know, technically this one is better, because if you think about that, if you kind of change nitrogen for a carbon, right? It's basically cis-trans isomerism is what we're asking there. So the trans is better than the cis. Okay. But again, super simple, right? We're just switching out N for that. I could have, again, that ketone that I drew earlier. I could do a really weird amine, this one here. I know Dr. Levens likes to draw very crazy molecules, but it's because she trusts your judgment, right? She trusts your ability to recognize that, hey, I am doing a very crazy reaction with crazy reagents, but actually that reaction is just a, this is just a very dolled up way of doing what I did before, right? With just a acetone and an ammonia, or a, methylamine, right? It's all the same. Again, there's cis-trans isomerism, so actually technically this should be the more correct answer, but who cares? Just draw either one. Shouldn't matter. Shouldn't be that big of a deal, unless you mentioned it in class, which I don't think she did. Okay. Now, once again, there is a type of this reaction, which maybe when I draw this snake of a molecule, you start to see it, right? There is a type of this molecule that can react with itself, intramoleculars, right? So don't forget about those. 1, 2, 3, 4, 5. It's going to be a 5-membered ring, and I will number because I know you guys like numbers. I'm not a very good number guy. I did really bad in math. Okay, and so you can imagine 1 attack 2, so 2 should be your carbonyl carbon. Again, what are we going to form? We're going to form an imine. So if 2 is the carbonyl carbon, and we're forming an imine, there should be a double bond between N1 and carbon 2. Okay, so we form that imine there. Man, the wind is so crazy. I don't know if any of you guys in the Bay Area or we're in the Bay Area. The wind is absolutely crazy today. I don't know what's going on. Anyways, all this changes if this were the 6-membered. I'm just drawing this in a different perspective, but it would just look like that. Okay. But if this were a ketone, we'll have this change. Just get rid of that H. Now it's a methyl there. Okay, cool. So imines, right? Kind of cool creatures there. Again, primary and ammonia, because in this reaction we go from NH3 to NH. So we're losing 2 hydrogens. Where are we losing them? We're losing one right here, and then we're losing another right here. So we lose 2 hydrogens, get out that imine structure. Okay, and so that's what makes NH3 and RNH2 similar to each other. Right, that's why we can kind of lump them together. These both make imines. Okay. Now, one last thing before we move on, amines are a little interesting. That pi bond is actually pretty reducible. If you just leave this in solution, usually amines will react with anything it comes into contact with. So we kind of, we don't want that. So what you usually see is usually an H2PD step preceding, or sorry, not preceding, but whatever after seeding would be. I don't know what that would actually be. What would be after seeding? Someone tell me afterwards. Anyways, what you'll usually see afterwards is an H2PD or some kind of reducing step. Another usual reagent is like NABH3CN or NABH4. It doesn't matter. The point is that some reducing agent. These 3 will work. One of these 3 will work. That just turns the double bond into a single bond. And you just add an H on the nitrogen. So reduction, this actually has a name. We call this reductive amination. I call it REDAM for short. But all you're doing is turning that single bond into a double bond into a single bond, and then you're just adding a hydrogen onto that carbon, onto that nitrogen to reflect that as well. Okay, so that's what the reduction does to all of these. Okay. These are really unstable in water, really unstable in water. It's if you even like cough on it, you basically compromise your product. Since I gave an earlier problem that was a little bit of a tricky one, I can give another one here too, that we can all solve together. But let's say I had this. This is called hydroxylamine, or methyl hydroxylamine. Right, so it's like kind of or we can go with the alcohol version. It's kind of half alcohol, half amine, and I have, let's say, an aldehyde here. Great question would be is if I reacted this. So usually hydroxylamine, you buy it in the hydrochloride salt version. So we do note that by saying this. This is just saying that it's salted. So it comes with its own acid. You don't have to add it in on your own. But we can go ahead and try this reaction out. Actually, you know what? Just so you guys can have an extra bit of connection with me, we can do it the way that I've done it in the past. I've actually done this reaction. This is the molecule I did it on. So if you want, you can pause and try this on your own, or you can move on. It's up to you. But the question is who is going to attack on the hydroxylamine? Is it going to be the nitrogen or the oxygen? The answer is it's going to be the nitrogen that does the attack. Between the nitrogen and the oxygen, nitrogen's more nucleophilic, right? It's more basic. It's more willing to give up its own electrons. So what we'll see is a formation or an attack by the nitrogen. Now this is an NH2, so we know it's going to form an imine. Okay, and in this particular case, we're going to form this imine here. Okay. There's actually a name for this kind of imine. This is called an oxime. And one really cool thing you can do with oximes is if you put these in a dehydrating unit or dehydrating solution, such as SiO2, they will transform. Oh, actually, I drew this wrong. Oops. This should actually be a 5-membered ring. The 6-membered ring is what the dehydration is actually going to do. So the 6-membered ring, this, if you're really, if you're really bored, I don't know why you would be, but if you're really bored, you can think about how this would happen. I don't know if you guys learned SiO2 actually, so maybe not. But yeah, this is a cool little reaction that you can do, that I've done for some of my research at UC Davis. Okay, pretty cool. So hey, now we've all kind of done the same thing now. Cool. All right. Moving on. So then what's the deal with secondary amines? They don't have 2 hydrogens, right? So what's going to happen there? Let's look at that real quick. Okay, what's going to happen here? Majority of this is going to be the same, so I'll just kind of speed through this a little bit, as in like I'll start from here. Right, so we'll have let me put this over here. Actually, it's a lot bigger. Okay, we'll have this, and then we'll have a proton transfer. That turns into water. Again, sorry, I'm just kind of going through this a little quickly, just for sake of time, and also just because a lot of this is the same as the other page, right? We'll have the loss of the water group there, and then we'll have NR2. Okay, and then once again, we're at this crossroad of, hey, I have this iminium, right? This iminium type, sort of like that carbonyl we looked at earlier. And again, we might want to think that, hey, I think those, another amine wants to add. But again, remember, amines are better bases, or they have the ability to be bases rather than being acids. Sorry, rather than being nucleophiles. So what's going to even happen here, right? What are we going to do? We're still going to act as a base, so that's part is retained. But where is the hydrogen, right? Where am I going to get a hydrogen from? Well, the hydrogen is actually going to come from this position here, the position right next to that double bond C. Okay? So we have a name for this. We call this the alpha carbon, and we'll talk about this probably in the next video because I want to segment this. I also, part of these videos is also just so that they can be used in the future, and I'd rather these be segmented than kind of erratically scattered, just following what the quarter is going as. Just have some organization. But we'll talk about this alpha carbon thing in the next video, and how that's useful. But the carbon that's next to the double bond carbon, called the alpha, and that's the proton we're going to take. Okay, and the reason for that is because when we do that, what we form is this structure here, which is a conjugated amine. Okay, the nitrogen is conjugated, or its lone pair is next to this pi bond, so it's lower in energy. Okay, form this conjugated amine we call an enamine or an enamine, whatever you want to call it. Okay, so we form an enamine. So this is a bit of an interesting reaction. Okay, so because we only have one hydrogen from the nitrogen, we can't dehydrate both. or we can't get both of our hydrogens for dehydration on that nitrogen, right? So normally we have NRH2, so we can get both of our hydrogens from the nitrogen, but in this case we only have one, so we get that one from there. We get rid of that, but we got to get a hydrogen from somewhere else. Best close source is that carbon there next to that iminium, or next to that amine, and we form the enamine. So predicted products are slightly a bit more difficult with these. I mean, with aldehydes, it's very simple, right? If I have an aldehyde, and let's say I have diethylamine, H+, very, very simple, right? I am doing practically the same thing. I can go ahead and get rid of the carbonyl and put the secondary amine there. I just got to put a pi bond next to that carbon, right? So the carbon that I attached to, it's that carbonyl carbon, just put a pi bond to that other carbon there. Make sure it's a conjugated amine. With aldehydes, there's only one carbon that you can do that with. It's that next door carbon there. So if you have an aldehyde, don't hesitate. And I hope on your exam, when you get this question asked, or your quiz, sorry, that, you know, Dr. Levens makes sure that your secondary amine is reacting with an aldehyde. Because again, it makes your life a little bit easier. Right, so we have this, get rid of that, put the secondary amine there, and then make a double bond with that adjacent carbon. Okay, so we can make cyclic amine and amines too. If I have a ketone though, and again, hopefully this ketone is symmetric, right? If I have a ketone, technically I have two positions that we can attack on. Now, like I just kind of mentioned, if it's symmetric, it won't matter, right? You can choose either one. So I'll just do these, I'll just do an amine. I'll do the secondary, I'll do the diethylamine again, right? In this case, it won't matter which one you put it on, right? Whether you put it on the left or the right, it'll be the same. But on the off chance that you do have to do this problem here, right? Where you have to figure out, you know, whether it forms. So in this case, we'll have this enamine, or we'll have this one, right? In the case that you have to choose between two regioisomeric products, so two alkenes that are different, go with the alkene that is more sub. So this alkene has 3 groups attached to it versus this one only has 2 groups. Go with the one that's more sub. Yeah, we'll go with the more sub position. Okay, cool. So tricky question, hopefully not something we have to worry about, but it's a possibility. So we'll just, you know, if we have to, just put on a note card. Just a bit of a blessing at this point, right? To be able to have that. Okay, cool. Now, again, like I mentioned, there are intermolecular types of these reactions. We've been mentioning that all day today, actually. 1, 2, 3, 4, 5. So you can imagine that I have something like this, which again, this is going to cyclize here. Skip some numbers. 1 attacks 2, then 3, 4, and 5. We got a 5-membered ring with a nitrogen in it, right? Let's say 1, 2, 3, 4, 5. Right, 2 is the carbonyl oxygen, which is going to have an OH then, or sorry, it would have had, but let's just go ahead and put the methyl here first. Right, actually, you know what? Let's go ahead and just put the OH here for now, just so we can kind of track this carbonyl carbon. Remember, this water is going to dehydrate, and then we're going to form a bond, but we're not going to form the 1-2 bond, right? That's going to make a nitrogen with 4 bonds. What we want to form is a bond with the nitrogen, the carbonyl carbon and one of the next door carbons. So if you want to, that's why it's, you know, helpful to put the OH here so you can kind of track where the carbonyl is. So here's where the carbonyl is. You want to make a bond either here or here, that double bond, right, to make the enamine. In this case, right, we can either have it here, 2, 3, which has 1, 2, 3 things coming out of it, versus 2 and this guy here, which only has 2 things coming out of it. So we're going to want the internal one. I want this one here. Okay, call it a day. You can also reduce these enamines too if you wanted to. So if you want to get rid of that pi bond, you can totally do it, because in solution, you're actually, remember, everything's in equilibrium. So even this iminium is possible. This iminium is just what's captured. Usually, in this case, you will use a hydride instead of H2, like NaBH3CN. And you can get that there. And in this case, you don't even have to draw in a hydrogen. You just got to reduce it. And you'll be fine. It's totally possible. You know, this actually makes me think of I don't know, this just came to mind. So this is a bit a little bit not off topic, but it just reminds me of a different type of intermolecular you can get with the alcohols. You can also get this type of intermolecular too. Completely forgot about this. So let's say we cyclize like that first. Yeah. So we'll make a 5-membered ring on that with the oxygen inside. So actually I'll do 1, 2, 3, 4, 5 like this because 2 is on the left side this time. So that you can see that when 2 on this chain with 1, 2, 3, 4, 1, 2, 3, 4. So 1, 2, 3, 4. Right. You can see that you can see a bit more clearly what's going to happen here. When this guy cyclizes in, it's going to attack here. Oh, right, because they're going to be an OH here first. Yeah, I forgot about that. That's going to attack in there. And so what this is going to make is 2 of these 5-membered rings. This is called a Spiro compound. Just came to mind. So interesting example. Kind of looks like glasses. But it's just something to know. Cool. All right. Sorry, I was just checking my phone really quickly. I got a new phone. Maybe I'll send a picture of it. I got this really nice case on it. It looks, I really like ube. So I got like a ube colored, like a, what do you call it? Like phone case. I really like it. I got a Pixel 6a. It was on sale for like $2.99, I think. And then I have a Pixel 5 that I'm just going to trade in for it. So probably get really cheap phone. Little rant, but I'm never going back to Apple. Some phones like these Google phones, like they do everything an Apple phone does, just like half the price. It's a really nice phone. Anyways, cool. My little spiel there. Cool. All right. So those are our oxygen and nitrogen additions. Okay. Again, we will see that with the primary ammonias, we'll make amines. These guys will make N-amines. Okay. Tertiary, we can talk about it if we want to, but tertiary is the reason why they don't even react at all is they don't even have a proton, right? For this, you need 2 hydrogens. You need 1 hydrogen on the nitrogen. This has 0, so it's just never going to react anyways. Okay, but these are the nitrogen reactions with carbonyls, and again, everything we described with ketones can happen with aldehydes too. Oxygens, again, remember, in acid, you're going to make acetals, right? Yeah, so I guess we can kind of quickly just summarize this. So alcohols and acid, right, will give you acetals. We're just replacing carbonyl with 2 OR groups. Primary amine and acid will just replace the O with NH. Sorry, ammonia will do that. Primary amine will replace N with O with NR. Secondary amines will replace the carbonyl with NR2 and then pi bond with the carbon next door. And again, if there's a regiochemical concern, always go on the more sub side. And then what else? I guess hydrates, but typically hydrates are unstable, depends on the equilibrium constant, not really a reaction per se, more of a tool. It's a nice tool to have. Like, in the higher classes, when someone asks me how reactive a certain carbonyl is compared to another, usually what I'll do is look at the hydration, and that will give me the answer almost immediately. Cool. Now, again, don't forget the intermolecular variance. Again, really, really, really getting this idea stuck in your head that this is a possibility to cyclize with all of these cases here. Yeah, cool. Now there's one last reaction. Now I just realized there's one last reaction we can talk about. Very, very simple. Won't take more than a second actually. The cyanohydrin, so NaCN HCl. This is just a really fancy way of adding CN to a carbonyl. Not really fancy. I don't want to say fancy. It's the safe way of doing it. Instead of just adding in HCN, because HCN is really toxic. It smells like almonds, but if you know that it smells like almonds, it's because you're going to die soon. So rip to all those people that figured that out, right? But this is a cyanohydrin, super simple. You're taking a carbonyl and you're replacing it with CN and OH. Wow, how easy is that? Pretty easy if you ask me, right? I think that's pretty easy. Only significant thing to know about this one is that you can usually reduce the pi bond on the CN. Two different ways of doing it. You can use a hydride source, usually lithium aluminum hydride, or you can use H2PD. In that case, you're just replacing CN with CH2 NH2. So super, super simple. So anytime you see this, these conditions, super, super simple. NaCN, HCl. Just replace OH and then CN. Okay, so that's that. I just remember that that was a reaction you guys needed to know. Cool. All right, so those are our additions, and for the most part, actually, these are all of our reversible additions, right? These are all the ones that we're going to probably spend the most time practicing. You know, those are all of our reversible ones, and then I'll go ahead and add the NaCN one here. There isn't really an intramolecular version of this, so don't worry about it. Nothing crazy there. Okay, cool. So the last bit that we can cover for carbonyls before we talk about the conjugated guys is just our reductions. And so these are our irreversible, strongly basic nucleophiles, our Grignards and our hydrides, and what these guys will do. Okay. But these reactions concern RLI and RMGBr. We'll start with the R groups first. So in this class, we've never really had a way to kind of combine two carbon chains together. Like, there's no way to do this, right? Combine those two and then make a longer chain. That's kind of the forbidden reaction. I mean, if we could do that, then we would. It would make our life really, really easy, right? We just stitch two carbons together. But that's not really easy thing to do. So what we normally have to do is kind of trick the molecules into doing that for us. Carbon minus is a very super strong base, so it's not very easy to mix. So the way that we trick the molecule into doing this is we take like an alkyl halide and we do something called a metal halogen exchange. So we can do it with the lithium, just throw in some lithium, and what it'll do is it'll switch the bromide for lithium. Another thing you can do is you can add an Mg in ether. And what this will do is insert magnesium between the bromide and the carbon. Both of these mean the same thing. MgBr and Li, they're both metals. Just think of them as like metal cations. In both of these cases, what we're really saying is that we have a carbon anion. Okay, so we have a nucleophilic carbon anion, okay, which is usually very basic. Usually very, very basic, this species here. Okay. Actually, here's a funny word of the day, or fun word of the day. Usually CBr, if you think about it, it's polarized towards the Br, so the carbon is positive. But when you add in these metals, the polarization switches, right? It turns into a negative. When you do a reaction that switches the polarity like that, we call that an umpalung. So if you want to impress Dr. Levens, I don't think she told you guys this, but if you want to impress her, you can write that on your paper, or, you know, just say it in her office hours or something. She'll be like, wow, this kid really knows something about it. Okay, but this is how we make our active nucleophile. And again, usually you'll have some kind of R group with either of the metals there. I'll just use Li this time. But essentially what you're doing is you're just attacking on the carbonyl with that R group. So you have a carbonyl. It becomes an O minus, and then attached to it is going to be whatever that R group is that you just added. Okay. Again, you'll usually quench this afterwards. And what you'll get out is an alcohol. So these reactions here will always afford us an alcohol. We never usually see more reaction than this. And in the case of the Grignards, what you're essentially adding onto them is going to be whatever the R group is of the Grignard. Okay. or the organometallic. So there's two names for this. Sorry, I've been saying it without. So this here is called the Grignard. When you use MGBR, Victor Grignard figured this out back in 18 whatever. And then usually like lithiums we call organolithiums or organometallic. Doesn't matter. Same thing. Okay. So again, it's just going to take some practice just doing these, and I imagine there's a lot of it. But the idea is whatever you have, right? You're just adding to the carbonyl. So in this case, what you'll have is, you'll turn that carbon into an OH, and then looks like there's a 3-carbon chain. So I'll just add a 3-carbon chain just like that. Boom, done. I'll highlight it so that you guys can see it. Let's say that I have this ketone here, and I add what can I add? Yeah, let's say I add this, or I'll put lithium this time. Again, all we're doing is we're adding this component then to the carbonyl. So I'll put an OH here, and then to the carbonyl, we're just going to add that 5-carbon chain, which I might have drawn as 6 on accident. There we go, just like that. Boom, super simple. Let's say I had this aldehyde here, and what I added to it was, oh, even this here actually. The hybridization doesn't matter. You can even add this. This is totally fine. Maybe you guys don't know how to make that, but that's okay. Actually, no, you guys do know how to make this. No, I lied. You guys knew how to make this. Because you guys know how to make benzyl bromides. Never mind. I take that back. You guys do know how to make this. You guys know how to make benzyl bromides. So you could make that if you wanted to. If you wanted to. Not that you have to. You could if you wanted to, though. Right, you're just turning this into an alcohol, and then you can just add this anywhere. As long as it's connected to that carbonyl carbon, you're fine. Okay, so Grignards are pretty simple usually. You're just adding on that group onto the carbonyl carbon and reducing it to an alcohol, right? Just make sure that you're getting the group right. I know a couple people are getting confused on what to add. Just kind of, if you wanted to, just erase the metal out of your brain, right? And then just like whatever that chain is left, right? That's what you want to add on, kind of what you want to think of it as. One last thing on this before we kind of move on, because not much more to talk about for this. Chiral centers are still a thing. Anytime you have a carbon with 4 different things on it, you just have to remember it could be chiral. So there's kind of 2 ways you can handle this. One way is you can just put plus minus if you think it's chiral. That will cover for both instances if it's in the plane bond. Or you can just add stereochemistry. So I can just add a wedge here or a dash. And that will take care of it usually. And then make something else like the opposite. Like I can make this a wedge and then make this a dash if I wanted to. Okay. But the plus minus thing is kind of a cheat code. If you wanted to use it, like you could just do plus minus here and that would work. Or if you wanted to, you could do wedge and then maybe dash here, and then just the opposite. And because inevitably this will be asked, does it matter which one I chose? Not at all. Doesn't matter at all. Who cares? Choose either. It doesn't matter who you made dash or you made wedge. Just choose one for one of these. Like I chose OH and H, and then make sure for the other one you switch it. Don't just like choose any 2 groups. Choose 2 and then make those the guys that are switching between the 2. Cool. Again, Organometallic's not too bad. Hopefully not too bad. Again, it just takes a lot of practice of drawing these out and you'll be fine. The hydride is even better. So I started with the harder one just to kind of start with that, but the hydride is even better. LiAlH4 and NABH4. Okay. These are even better because all they're really doing, I have, let's say, an aldehyde here, and I add in NABH4 in methanol. This is the solvent, by the way. I know that some of you might see this and get confused and might think it's an acetal. Remember, acetals are an acid. They're not in sodium borohydride. So this is definitely not going to be acetal. This is just solvent in this case. But NABH4, you just want to think of it as H minus. But what's attacking is H minus. So if H minus is what's attacking, Sure, I can draw it out like that, but this is also just equivalent to this. Okay. Or if you think about it, all you really did was you turned the carbonyl into an OH. Hydride reactions are the simplest. And it doesn't matter if you do it with lithium aluminum hydride or you do it with sodium borohydride. You are simply, if you want to think about it as an easy way to solve the problem, turning that carbonyl into an OH. That's it. This is a correct answer. I know it looks weird, but it is a correct answer. If you wanted to, you could put an H here and make it a little more correct. That's it. Okay. Say I had this guy here, and I did NaBH4, CH3OH. I'm just turning that carbonyl into a single bond. Again, just make sure for chirality, right? This will be chiral, so you could do plus minus here if you wanted to, or you could just draw both out. Right? That's a possibility. Okay, so super simple. Okay, a way to think about this is that these reactions are the opposite of chromic acid oxidations, right? So, for example, I could start with, let's say, a simple alcohol, and I could do CrO3, right? That would turn this into, or let me do PCC. PCC, that would turn this into an aldehyde, right? But if I wanted to, I don't know why you would want to do this, but let's say you realize you made a mistake, you could go back and say, oh, I do NaBH4, right? I go back to what I wanted to. So the hydrides are kind of like a, opposite reaction. They're not actually the opposite, but they are like an opposite reaction to the oxidation. Okay. You could also do, let's say, from the PCC aldehyde, a Grignard. So let's say that I wanted to add in MgBr. Right, again, I can just draw this. All I'm really doing is turning this into an alcohol and adding this on here. And now I get an alcohol with the new chain on it. So instead of going back to the original alcohol, I went to a new alcohol. I went to butanol. Okay, I went to butanol. Well, hey, guess what? This butanol can still be oxidized, so I can do PCC again. I turn it into butanone, and then I can do another Grignard. Or maybe I can do a reduction, right? It's up to you. So kind of understanding how to picture this. Again, it doesn't matter which one I use. I'm just kind of riffing here, choosing whichever one I want to. No big deal. Right, but I can go ahead and add this in. Again, just turn this into alcohol and then just adding what it is on that Grignard, or that, in this case, the organolithium, the organometallic. Okay, cool. So that's a way to think about those. The reductions are usually very, in my opinion, very simple once you've gotten a handle for them. It's not too bad. Okay. Now, one last thing that I'll just mention, you might have noticed that for NaBH4, I kind of added in methanol together, and lithium aluminum hydride, I added in the H3O plus second. Right? Why is it that I did that? It's because lithium aluminum hydride is very, very reactive. You can look this up on the internet. Videos of people putting it in water and it kind of just explodes. But this is super, super reactive, super basic. Okay. It does not tolerate protic solvents. So LiAlH4 does not tolerate protic solvents. So what that means is that if there's any water, if there's any alcohol in the flask with the aluminum hydride, it is going to absolutely eviscerate the reagent. Those two are going to react so fast, and you're not going to get a complete reaction. If anything, you're going to get a fire. So you basically make a hand grenade if you do that. So super basic lithium aluminum hydride just cannot tolerate that stuff, and it just, you have to keep it separate. Usually, what you'll do is you'll add in an ether, something that's not very reactive. Remember, ethers are not reactive at all to base, so very good solvent. So you'll see ethers like THF, like this one here. This one is a bit milder, more tolerable. So you can do it in things like methanol, and it's totally fine. You have nothing to worry about. Okay. So lithium hydride, it's stepwise because of that function there. NaBH4, not very tolerable. Which actually, that makes me remember, I didn't talk about this for this one either, right? For Grignards, it's actually kind of the same thing. It's actually a stepwise thing as well, because Grignards, not tolerable. These are not tolerable towards protic solvents. So here's a very cool, problem that you could get. I'm not sure if you would, but you could get it. But you could be asked, what would happen if a Grignard had to react with this hydroxy ketone? So let's say that I had RLI here. Where would the hydroxy ketone react? Well, again, you would think that the hydroxy ketone would react at the ketone, because that's what an organometallic wants to attack. But again, we are not able to tolerate anything with water or anything with alcohol. So actually, the first reaction will be on that alcohol here. We'll get an acid base that's super, super fast, rather than getting that addition onto the carbonyl. Which, if it, in some cases it's an issue, some cases it's not, because sometimes you can just put a lot of this and you can get the reaction anyway. So let's say that I had excess of this reagent here, it wouldn't have mattered, because this will just still add on. There's excess. But if there's like one equivalent, right? The first equivalent always goes on the alcohol as a base, and then the second equivalent goes on that alcohol there. Okay, cool. So a bit of an advanced problem, that one. I don't think you'll get something like that unless you talked about it, and I'm not sure if she did. I didn't see any indication of that anyways. Okay, so another way we call this a quench, right? You don't want to accidentally quench your Grignard or quench your lithium hydride. So you just make sure that there's absolutely no water or product thing at all. Again, with these guys, you would use something like THF. THF is the usual suspect in these reactions to kind of help not have these problems. Okay, cool. Actually, speaking of which, that reminds me, I did forget one really big thing that I think about it. Before we move on to the conjugated carbonyls, this reminds me, this whole idea that water can play a role in these reactions is actually really big in all these reversible reactions. And every single one of these reversible reactions, whatever you make, water will always reverse it. So let's say I have an acetal and I'm an H plus H2O. Water will reverse this reaction back to the carbonyl. So you essentially just get rid of whatever the structure is, acetal, or even hemiacetal, right? Whatever it is, get rid of it and you return to the carbonyl. Water is the reversing agent in these cases, and it doesn't matter what it is. It could even just be an amine, right? Water will turn the N into an O. Okay. Amines are a bit more difficult to see. So what I would recommend is thinking about it this way. But for an amine, keep track where that bond is to the nitrogen. But you just kind of want to get rid of everything. And then you just cut on, or you just return it back to the carbonyl like that. Just again, keep track of where that bond is to the nitrogen. Okay. I guess if you wanted a way to think about it, you're essentially cutting here, right? You're cutting on that heteroatom bond, that carbon bond to the heteroatom, and you're returning it back to a carbonyl. That's essentially what you're doing. Okay. So we call this hydrolysis, and hydrolysis will always return back to your carbonyl, as long as it's still the carbonyl derivative, right? So as long as it's the direct results of these reactions, because that's where it's reversible. Obviously, if you go ahead and you reduce this, so if I reduce this into the amine as such, this cannot be reversed with water, right? You cannot go back. You've already made a step that you can't reverse. Same thing with these guys, right? If you reduce any of these guys into the single bond, right, as such, so either as this or as this, you cannot go back. You've given up reversibility. Okay, so reversibility only exists for these direct, guys with the double-headed arrows, and they'll go back to their carbonyls. Okay, so my apologies, I forgot to mention that, but now I have, so that's good. Cool. All right, so one last thing, and then we'll call it a quits. We just talked about ketones and aldehydes and their reactions with nucleophiles. So one last thing we can talk about is the carbonyl with an alkene adjacent to it, or what I call the enone. Okay, so that's what we'll call this. So again, the alkene moiety next to the carbonyl. This is what's important. This is not the same as this here. This would not be the same. What's important is that the carbonyl and the alkene are next to each other. Why is that? Well, when they are next to each other, the p orbitals of that carbonyl pi bond and the p orbitals of the alkene can all overlap, and we get resonance. Okay, or delocalization, which results in resonance between those electrons. And so if I were to kind of draw out how this resonance would work, right? Again, we know how the ketone resonance works. That would make O minus plus like this. The alkene, though, when it decides to resonate, it's always going to resonate towards that carbonyl, right? Because it wants to fill in that cation there. So what we'll get is this here. Okay. Which reveals to us something new. Before, where we just had a ketone, right? That ketone always just reacted at the carbonyl center. So we always have reactivity at the carbonyl center, right? That's always a given. But with this new adjacent alkene, we now have reactivity at the farthest away carbon from the carbonyl, or what we call the beta carbon. So if I call this alpha and beta, where alpha is next to carbonyl, beta is farther away, right? The beta carbon is our new center of reactivity. Okay, we can now get nucleophiles that add into the beta center. So what determines where we get addition? Well, if I am to look at these two, or if I were to look at these reactions, okay, if I think about which carbon is initially more reactive, right, it's just a function of who's closer to the carbonyl, right? This carbon is closer, so every nucleophile in existence will add to the carbonyl initially. Okay, so every single nucleophile that you guys will see in this class will always add to this carbonyl. Okay, it's just the most reactive center. You just can't stop that. It is kinetically the most favorable addition. We call this a kinetic addition. Now, for nucleophiles that are super basic, like we talked about, so those irreversible nucleophiles, R minus and H minus, this is always going to be your addition. It's always just going to be here. So if you see LiAlH4, NaBH4, or you see RMGBr, or you see RLI, this is always where the addition is taking place. No doubt about it. Okay, so if I see an enone, right, and this is kind of a disguised one, but that is an enone there, and I see ethyl, lithium, I know that what this reaction is going to do is add on to that carbonyl center, and I'm not batting an eye. And again, plus minus because this could be wedges dash, whatever. Okay, kinetic addition. These are super, super basic usually, so super basic. And a good rule of thumb is that their pKa is usually greater than 30, or I think 20. I don't remember. I'll use 25 in the middle. Okay. These are kinetic additions, kinetic nucleophiles, irreversible. Okay. But there are nucleophiles that are reversible. So there are some nucleophiles that will, hey, instead of always going this way and staying there, some of them will remove themselves from that carbonyl, and they will reverse back into starting material. And instead of staying on, or instead of attacking on that carbonyl center, they will instead attack on that beta carbon. And what we get instead is a different product. This product here. Virtually every single nucleophile that is not these two is going to do this type of reaction. That is why I just tell you guys, remember these four here. If you do not see these four, you know the nucleophile is going to add at that beta position, without a doubt. This is what we call a thermodynamic addition, because you give the system a little bit of time to think, and it thinks, oh, I don't actually want to stay on that carbonyl carbon. I actually want to remove myself and add myself somewhere else. Okay, everything else does this. So you can think O minus, NH3 or NR3, OH, SHCN. I mean, really, anything will do this. If you do not see R minus or H minus, you assume it's going to add to that beta position. And this reaction is as simple as just getting rid of the pi bond and just adding on that beta position there. So let's say that it reacted with cyanide. There you go. NaCN, that's where it goes. I'm not even hesitating. Again, you could plus minus if you wanted to. That's up to you, but that's all I will do. Okay. Let me go back here and let me just erase this. You can do a couple more of these. Let's say I have this and I react with NaBH4. Again, this is the easiest reaction, right? Because what is all we're ever doing? Anytime you see it NaBH4, again, that's one of those 4 nucleophile. It's only to do direct attack. Oh, that's another thing. This is called direct. This is called conjugate. Okay, but it's going to do a direct attack. This is going to turn this into an H, sorry, into OH, and that's it. Not even stressed about that at all. But hey, if I turn this into ethane thiol, guess what? Ethane thiol is going to add on that beta carbon, keeping that carbonyl intact. Okay, absolutely intact. Okay. Now, mechanistically, there is a way to do this. Just look at your notes. I kind of want to call it here. I'm getting a little tired. And that's something, I mean, mechanism is something that you can just write down in your notes. The general idea, I mean, we've already seen the carbonyl addition and what the mechanism is. For the conjugate addition is very simple, right? Generally speaking, the nuke just attacks here. Electrons sink into the carbonyl. And then instead of protonating at O, what will happen is this O minus will swing down and it'll protonate at the carbon. So whatever hydrogen source you have, it'll do that. So that's usually what you'll see. Okay, so that's the generic mechanism for that. I'll put on the side here. But again, use your notes to guide you mostly on this because I'm just being really lazy right now. But yeah, cool. Again, we can do many examples of this. I'll do one more just for the sake of doing it. But really, there is no like craziness here, right? If it's organometallic, add it to the carbonyl. If it's not that, and it's not a hydride, you just add it to the beta position, just like that. Okay, so just I mean, we're doing so many of these in like 2 seconds. It's just that's all we have to do. So either here or here, right? Just depends on what you have. Okay. What's really funny is that actually you guys won't even learn how to make this until the next like unit, I think. So it's kind of fun. Normally you learn how to make these enone structures and then you learn how to add to them. But for some reason in this class, they don't do that. Cool. All right. So with that being said, then this is going to be the end of this video. I apologize if I got a little rushed at the end. I just wanted to, you know, I said I wanted to finish before like hour and a half, but it definitely hit about 2 hours there. So apologies on that. But I mean, that's just how it rolls with this. I think every video is just gonna be up to 2 hours now. Just a little bit sad, but it's okay. Okay, cool. So yeah, if there's anything I missed or anything I messed up on, please let me know. Again, this is generally serving as a way to fill in some holes that you might have. Use your lecture as your primary material. Get your vocab from your lecture for sure. If there are any questions, please let me know. You guys have a good night.